Today, more than ever, radio frequency signals, or RF as it's commonly called, is used to transmit all types of information. Starting over 100 years ago, wireless transmissions were first broadcast carrying Morse code. That was followed by audio and then television broadcasts. Later still, cordless telephones, remote controls, cellular telephones, cable and satellite TV, and now data in the form of Wi-Fi, Bluetooth, WiMAX, as well as 3G and 4G networks. The common link between all of them is the use of RF, or radio waves, to transmit and receive information. But what is RF, and how does it work? Radio frequency signals are made up of electric and magnetic waves. Thus, they are referred to as electromagnetic waves. The two waves, or fields, vary in intensity over time, forming two separate but related waves that are perpendicular, or at right angles to each other. Whenever the electric wave is oriented vertically, the magnetic wave is oriented horizontally, and vice versa. Because the electromagnetic waves have a distinct orientation, they are said to be polarized. The polarity of an RF signal can be horizontal, vertical, or even circular. RF is said to radiate and is referred to as electromagnetic radiation. But unlike nuclear radiation, which is harmful, radio waves are non-ionizing. The energy they contain is at a much lower level and is not capable of ionizing atoms, which is what makes nuclear radiation dangerous. So while electromagnetic radiation will cook your food inside your microwave, it is not radioactive. How quickly the electric and magnetic fields vary in intensity, or oscillate, determines their frequency. If a radio wave passes through a complete cycle 100,000 times per second, then its frequency is said to be 100,000 Hertz. Radio waves travel at the speed of light, and the distance traveled during one complete cycle determines the wavelength of the RF signal. Lower frequencies have longer wavelengths, while higher ones have shorter wavelengths. Due to the fact that RF travels at the speed of light, or very close to it, the wavelength of a radio wave can be determined by dividing the speed of light by the frequency. As an example, an RF signal with a frequency of 870,000 Hertz has a wavelength of 345 meters. The wavelength of an RF signal is very important, as the physical shape and size of components used affect the RF signal based on its wavelength. The scientific term for wavelength is lambda. Antennas emit and/or absorb radio waves. Based on their structure, they can shape and focus RF waves, providing gain or amplification to the signal. The antenna, its apertures or elements, must match the wavelength to efficiently pass the radio waves through it. The better the match, the higher the efficiency. There are many different designs for antennas, from a simple wire hung between two trees to a broadcast antenna that weighs several tons and costs $250,000. Some are as tall as towers, and others fit inside your cell phone. Their shape and size all depend on the wavelength used and the purpose of the antenna. That 870 kHz RF signal mentioned earlier is the frequency used for one of the channels in the AM radio band. In order to broadcast this signal, an antenna is required of the correct size for the frequency's wavelength. An antenna of the same height as the wavelength would be 345 meters tall, or 1,113 feet. This would make a very impractical and costly tower to build. This happens quite often in the lower frequencies of broadcasting. The full wavelength makes it impractical to build the equipment, so smaller, more practical-sized components are constructed. Using a fraction of the wavelength, the most common ones are 1/4 and 1/2 wavelength. In the case of the AM station's antenna, 1/4 wavelength is used, and the antenna becomes more manageable 86¼ meters, or 283 feet. Many antennas are placed on top of or on the side of a tower, but for AM stations, the required height is so great that the tower becomes the antenna. Of course, higher frequencies have smaller wavelengths, and it becomes easier to make components for these frequencies. For example, an RF signal with a frequency of 23 gigahertz has a wavelength of just 13 millimeters, or just over half an inch. Antennas provide gain by the shape of their pattern. An antenna's pattern specifies the direction with which the antenna will absorb or emit RF. These are called directional antennas, and a wide range of patterns of coverage are available. Directional antennas are used for both transmitting and receiving RF. Transmitting from a directional antenna saves power and reduces interference by covering only the desired areas with the RF signal and reducing or eliminating the RF in undesired areas. When using directional antennas for receiving RF, they can block interfering signals and increase the amount of RF signal making it to your receiver. At an AM radio transmitter site, you may see more than one tower. The multiple towers are lined up in a row and together make up a single antenna for the AM station. The multiple antennas function to aim the transmission of the station's signal in a particular direction, such as towards the nearby city. This makes it a directional AM station. Radio waves are thought of in one of two different forms, either as waves or as particles. Which one depends on what scientific principle you're trying to prove. Radio waves propagating through air are best thought of in terms of waves, as we have been discussing here. RF can travel through many environments, such as air, the vacuum of space, walls. They just don't travel well through very dense materials, such as concrete, water, dirt, or metal. With that in mind, different frequencies of radio waves behave differently as they travel through the air. Surface waves, also called ground waves, are in effect for AM broadcasting. This is where the radio waves follow the curvature of the Earth and are capable of traveling great distances. This only works with low-frequency radio waves, up to about 3 megahertz. Often you will see AM towers at the water's edge on a lake or bay. The moist ground and the nearby water makes for a very conductive ground plane, which is important for AM broadcasting. Low frequencies tend to follow the curvature of the Earth as they travel, so a low resistance connection to the Earth is very important at the transmitter site. Then there's line of sight, where the RF waves travel in a straight line, and the transmitting and receiving antennas must be able to see each other with no obstacles in the way. The limiting factor for line of sight is the curvature of the Earth's surface. The point at which the signal can no longer be received is called the radio horizon. The radio horizon can be extended somewhat by elevating either or both antennas. This is one reason antennas are positioned on top of hills and mountains. Atmospheric conditions affect the way in which radio waves propagate through the air. Heavy rain can absorb certain high-frequency radio waves because their short wavelengths allow them to be absorbed by large rain droplets. Microwave links in the 23 GHz band can fade out totally during times of heavy rain, for example. Certain frequencies of radio waves are capable of bouncing off the ionosphere. This can extend their range by quite a bit. The ionosphere's height is affected by the solar winds, and during the night the solar winds pass around the Earth and pull out on the atmosphere, thus raising the ionosphere. Some materials absorb radio waves, while others reflect or refract them. All can cause problems when trying to receive an RF signal. Foliage tends to absorb radio waves. In fact, an antenna that once received a perfectly good signal may experience a signal loss as trees grow in front of it. Tall buildings tend to reflect radio waves, causing them to scatter in various directions, sometimes extending the range of the broadcast and sometimes interfering with it. Another important factor in the propagation of radio waves is path loss. As a signal moves further from its source, the intensity or signal strength is reduced. In fact, for every doubling of distance traveled, the signal strength is reduced to 1/4. In general, lower frequencies travel further than high frequencies. As mentioned earlier, RF signals have a polarity or orientation relative to the transmitting antenna. The position of the antenna to the Earth's surface determines the orientation of linearly polarized radio waves. By matching the receive antenna's orientation to the polarity of the transmitted signal, a higher received signal strength will be achieved. When the transmitting and receive antennas are at cross poles, meaning they are of opposite polarities, the received signal is reduced. While traveling through the atmosphere, radio waves can have their polarity altered or shifted. An RF signal's polarity may become tilted by several degrees, making it harder to be received since it no longer matches the orientation of the receive antenna. To reduce this effect, some broadcasters transmit both horizontal and vertically polarized radio waves. This is called circular polarity when both power levels are equal. Sometimes it's the desired RF signal itself that causes the interference. A transmitted RF signal can bounce off walls and buildings and reach the receive antenna from a different angle and at a different time compared to the direct signal. This is called multipath interference. Because of the different paths the two signals take, they arrive at different times. Multipath is the cause of many RF reception problems. This has been an overview of what radio waves are and how they travel, and some of the obstacles they encounter on their way from the transmit antenna to the receive antenna.